In the second part of the lecture, we will show how to fit multivariate linear regression model using gradient descent, and also how to evaluate performance and recognize overfitting. If the number of features is large, for example, 100,000 features, normal equation is impractical because we have to invert a very large matrix. So instead, we can use gradient descent. And gradient descent is an iterative method. So we always have to start with some estimate of our solution, which is the weight vector W, and update this estimate. So you see here that n or n plus 1 refers to iteration, and we will update by adding the negative derivative with respect to W that we already calculated previously, multiplied by the learning rate. Now it is very important to set the learning rate well, because if it's set well, then it will converge nicely to the solution. But if it's too small, then it will not get to the solution, or it would take a very large number of iterations to get there and take very long time. And if it's too large, it will oscillate around the solution. Also, there are several types of gradient descent. The classical one is called batch gradient descent, and it uses all the training data at each iteration. And if we have lots of training samples, then it can be very slow. Stochastic gradient descent is fast because it uses only one random training sample at each iteration, but as a result, it can be unstable. And you can see that in this plot, that it can also oscillate around the solution. Then a good compromise between these two approaches is a mini batch gradient descent, and this is actually commonly used even in deep learning. This type of gradient descent uses a subset of training data at each iteration, and you can see that it's a little bit more noisy than the batch gradient descent, but tends to converge nicely to the solution. So scikit-learn offers an object called SGD regressor, which means stochastic gradient descent regressor. And this object implements various regression models and feeds them using, of course, stochastic gradient descent. And if we want to fit a simple linear regression, we can use squared loss and no penalty. If we change the type of loss and type of penalty, we will get different models. So you can see that if we feed the model using just model.fit as usual, and if we plot the intercept and the coefficient, we will get again one intercept and 6 slopes. If this is application of the data set with 6 brain tissues. But the solution is slightly different from the one that we got through normal equation, even though it's still quite similar. And this is because of the randomness of this type of fitting. Now, how do we evaluate the performance of regression models? So we already have seen we can do that using R2 score, and R2 score measures proportion of variance in the data explained by the model, and perfect fit results in R2 score equal to 1. So this is the equation for the R2 score. So we see that we are comparing the expected target values with predicted target values. So this top part corresponds to unexplained variance, which is actually equal to the residual squared error. And the bottom part corresponds to total variance. So this is just the mean of all the data, as you see here. So these two expressions should be actually divided by number of samples so that they correspond to the variances, but these two factors will cancel out. So therefore, we don't really need to put them in the expression. So once we normalize the residual error by the total variance, we get the proportion of unexplained variance. And if you take 1 minus this expression, we get the variance, proportion of variance explained by the model. So we've already seen how to implement this in scikit-learn, so we'll quickly review that here. So first we will fit the model, and then we can use model.score to calculate the R2 score. So here we calculated on the whole set. Of course, we can do it, we can fit on training set and predict on test set if you want to evaluate the performance of the model. Then if we want to calculate cross-validated R2 score, we can use function cross-val score as we've seen before, which will give us arrays of R2 score, array of R2 scores, one per each fold, which we need to average. So now we are ready to explore what happens if we increase the number of features in multivariate linear regression. So if we measure the R2 score on the whole data set, we see that it increases with increasing number of features. But this is the same situation as we had with polynomial degree, because we cannot really say whether the model is improving or whether we are overfitting. So what we need to do, we need to use cross-validation to measure the R2 score. And we can see here that if we increase from single feature to 6 features, we actually improve the cross-validated R2 score. We achieve 0.89 now, but it will decrease again with 86 features. So we have 0.68 only, which is quite low. So from that, we can see that the best performance was achieved for 6 features, and we overfitted for 86 features. Now, we have another way of measuring performance of a regression model, and this is using root mean square error. So this is an average error between, again, the expected and predicted target values. And this error is in units of the target value. So in our example, it's age of the baby. And the perfect fit would result in 0 root mean square error. Now, this is how we implement it in scikit-learn. So scikit-learn offers a function mean squared error that calculates the mean square error between the expected and predicted target values. So before using this function, we have to fit the model and predict the target values, and then we can fit this into mean square error. So in this code here, we use the whole set. So this is mean square error of the whole set. Of course, we need to take a square root to get root mean square error. If we wanted to measure the performance of the model, we could, of course, fit on the training set and predict on the test set. And we see that the root mean square error was 1.12 weeks in this case. So we can also calculate cross-validated root mean square error. And this is again using the function cross-val score. But we need to set the parameter scoring. And there is an option negative mean squared error for this parameter. And that's the one we will use. So because this mean squared error is negative, we need to put a minus in front of it after we calculate the average, because of course it returns one score per each fold, and we have 5 folds, so we need to average. Then we take the minus to make it positive, and then we take the square root, and this way we get cross-validated root mean square error. So now let's see what happens if we measure the performance using root mean square error. So on the whole data set, we can see that root mean square error decreases as we increase the number of features. But again, when we use cross-validation, the error will decrease from 1 feature to 6 features, but then again increase if we use 86 features. So we can clearly see that the best performance is again using this measure for the model with 6 features. It's 1.27 weeks. And with 86 features, we overfitted because we have a large error of 2.08 weeks. So we've seen that we got to the same conclusion using the both scores. So what's the relationship between these two ways of measuring performance of a regression model? Both of them are related to sum of square errors, which is our loss function as well. And it's shown here. So it's sum of square errors between expected and predicted target values. But R2 score is normalized and therefore comparable between different models and dataset. On the other hand, root mean square error is interpretable as it is expressed in the units of the target values. In our case, it's age in weeks. But otherwise, you see that these measures are very related to each other. So we have seen that including more features does not necessarily improve the performance of multivariate linear regression, and this is due to overfitting. So how many features or samples we should have, what is ideal? So let's think about that a bit more in depth. So we know that we need to find the parameter models W using the normal equation, and we need to invert this matrix X transpose X to do that. And this matrix is a squared matrix of size number of features plus 1. But because the matrix X is n times d plus 1, which is number of samples times number of features plus 1, the rank of this matrix cannot be larger than n. And this is very important to realize. So it's possible that in some situation this matrix will be singular. So if it happens that we have less samples than we have features, that's when the rank will be smaller than the full rank, d plus 1, and then we cannot invert this matrix because it's singular. And in that case, there is no unique solution to this problem. So there are many solutions and we pretty much cannot really solve it. Then if we have just slightly more samples than features, then this matrix will be very likely invertible, but we might overfit to the noise in the data. And finally, if we have significantly more samples than features, then the regression will work well. So from this, we can conclude that we can decrease overfitting by increasing the number of samples in the training set. So size of our training set is extremely important for the performance of the model. So this is the end of part 2 of the lecture. And now is again time to test your knowledge. So there is a second quiz for you, which is called Multivariate Linear Regression 2. Please solve this quiz on kids and submit your answers. And after you're done with the quiz, please watch the part 3 of this lecture, Penalize Linear Regression.